doing some data analysis without actually knowing a whole lot about the data set. We're gonna focus on IDS events in particular, but that's kind of on a tangent to the usefulness of visualizing large sets of information. Typically, if you're looking up on the screen here, you don't have to know that there's any IDS events. You can pretty rapidly look at what's happening and see stuff that's anomalous or pick up details that you might not be able to see. As a reference point, there are something on the order of 400 or 500 million IDS events on the projector right now. All of them represented. They may be overplotted a little bit here and there, but you can delve down and get to all of them. So you're looking at 7 days worth of global IDS data. Pretty easy to pick up on stuff that I want to go look into without knowing what tripped, without knowing what was going on, without even knowing that it's security information. It's the old highlights game, kind of, find anything that doesn't belong. And so we're going to cover a little bit of the theory of how to set up a visual system. This is commercial off-the-shelf tools that was set up to do financial analysis that we've kind of subverted and started using for security analysis, doing some data massaging on the back end. The IDS analysis is kind of basic. I know everybody doesn't really need to hear it. The visualization, there's actually some principles that are really helpful when you're looking at large data sets. Presentation, usability, data structure, all that. Once we get through kind of the boring stuff, we'll go into and actually go through a live demo with a fairly global set of IDS events and look at how to use visualizations to find information about data. Quickly, I'm not going to cover coding visualization tool, what the actual implementation looks like, stuff like that. All right, so if we're doing event visualization, and really any sort of exploratory data analysis, we want to be able to really quickly and easily search a large amount of data to find the important events. That's really important because there's lots of systems that people have developed that will give you exploratory data analysis ability, but they're hard to use. Doing analysis is somewhat difficult. I'd like to spend my time understanding the information I'm looking at rather than using the tool. So being able to quickly use it, easily use it is really important. You wanted to actually see the incidents versus events. If you just wanted to see one line of information, you just look at text. You want to see the whole picture. Typical display solutions aren't that useful. We'll also use visualizations to remove noise. Reduce analysis learning curve. When I'm training people to do analysis, a lot of them will get caught up on what the event says, whether it's a router log, an IDS log, really any piece of data. And from my perspective, I'm really interested in having them just understand you're looking for unusual stuff. You're looking at stuff in the noise, and don't get caught up initially on the specifics. Okay, so the short list of what's wrong with IDS is most people are pretty familiar with these. They tend to assume that each security alert generated by the system correlates to an actual security event. I mean, they're intrusion detection systems, after all. So everything they send up is going to be an intrusion. That's problematic. The signatures are too broad. They look for one thing, they catch 300. They don't really tokenize activity very well, typically. The network isn't known. If I'm looking for something unusual, or bad, good, whatever, in a data set, I kind of, the IDSs programmatically need to know something about the data set they're looking at. They're not very good at doing kind of ad hoc pattern matching. And the other piece is, IDSs typically don't have a good concept of timing, volume, event combination, basic stuff that a human would be able to look at, but it's difficult to do programmatically. So basically, individual events can't be relied on to provide the whole picture. You end up looking at events that don't look at hostile activity. They're part of patterns which can't be recognized by looking at small groups of events. And they're still identifying specific behaviors instead of an incident. If somebody goes and buys a bottle of Ephedra or something from a gas station, they're just buying a bottle of Ephedra. If they buy 200 from 200 gas stations in an hour, well, they're probably going to make meth or something. That combination of time and volume is far more interesting than just the one activity. And that's the one activity that your IDS will typically pick up on. So the result of these problems is you really need some context, and visualization is really good at doing that. People are really good at looking for patterns that computers aren't. It can take me hours and hours and hours, days to code even, or something even rudimentary for looking at some of this data and coming out and making intelligent decisions about it. So human analysts have to be able to conceptualize what's going on, and it has to be quick and it has to be easy. So what you're building to do that is some sort of an anomaly, like a confidence system to look at the patterns and a system to look at the context. I see this one event, I don't have much confidence in its goodness, its badness. If I look at 7 days worth or a month's worth or 2 months worth, suddenly I start to have context. Suddenly I start to have context in what I'm looking at. You can use metadata if you take events outside of an IDS to kind of get an idea of what's going on. That's time, volume, history, etc. Again, you could do it programmatically, or you could display data in a way that allows people to look at it all. And you have the computer display information, which it's very good at. You have it calculate information, it's very good at. And you leave that final step of actual analysis to somebody else, some actual human brain. Looking at network data, and typically what we look at in a global scale, it's too varied to find anything interesting in it. The attack vectors are infinite. The purposes of the network are nearly infinite. So even if I coded something, it still needs some sort of confidence and verification system anyway. Again, people are better at seeing this than computers are. You could look at that screen we looked at initially, 10 seconds and you solve the important components of it. That would be a lot of work to have to make something do repeatedly. You can also use visualizations for data mining. And we'll go through some examples in a bit. Typically, I'll look at a data set prior to knowing anything about it, just to see relationships that I might not see in a single line or in an hour. I'll look at a month and be able to pick out stuff that that I've been working with the same data set for 3 weeks and never saw, just looking at one line at a time, or 1,000 lines at a time. As soon as I see 400 million of them, stuff kind of pops out. Theoretically, you can also do packet protocol anomaly analysis. I don't have the references with me, but I've seen some people do some interesting things with just visually understanding the protocol prior to looking at it. You kind of look at which fields change over time, how long, and just displaying that. And again, obviously, trending is visualization use. Let me go into, actually, wait. So, frequent tuning, obviously. What makes the visualizations for us, and by the way, we've operationalized this, is what's interesting about them is that you can rapidly deploy them, maintain them, develop them. Over time, if we see the same patterns happening over and over, we do the same analysis, we'll code it, we'll put it in a system, we'll automate it. But initially, if I want to look at something different, it can take me 15 seconds to reevaluate the data in a different format. So text, obviously, you just have too much resolution, or you don't have enough space for it. At this resolution, I've gotten 1,000 data points on screen at once. 1,000 versus 400 million is no contest. 1,000 rows of data in some of the networks we watch is a minute. That doesn't tell me anything about what I'm looking at. And again, it's difficult to reposition data when it's text. It's not apples to apples. Each line is different. So a lot of people, when I talk about visualizations initially, are like, well, 3D, cool. 3D actually is used to simulate real space. It takes up pixels. You lose resolution when you use 3D, and you also make your analysts think about what they're doing a little bit harder, because it really isn't 3D space. So these guys have to think, rotate it. Okay, well, there was some data back there behind that other information, and they still have to go through a manual process if it's 3D. If you need to compare more data points than you can fit in a single visualization, you just use multiples. That way you're looking at all of the data at the same time. some people, I'll look at a lot of demonstrations when I'm doing this of people who have like point-to-point boxes where you have, 5 columns of data and the lines are all drawn between the points. And that's fine, and we use them, but as soon as you put a whole bunch of data on that, you lose resolution, you can't see it, it gets overplotted to the point of uselessness. Same with data constellations and some of the other graphs. Just not enough data depth. So some of the really core graphs we've seen were actually located in the same government presentation. And this kind of illustrates what we're going through. All right, that's neat, but it doesn't tell me anything. That's 1, 2, 3, something like 10 points of data. I don't have to visualize that. I can remember 10 lines. If I can, I shouldn't be doing this. Again, this is neat, but there's almost no information there. I'm not sure why somebody would go through the trouble of plotting this type of thing out. Okay, this looks cool. You have all these things talking to each other. You don't know what they are. You don't know what the relationships are. You don't know what they're doing. And as soon as I plot any more than that, I lose track. Even with this many data points, I know that these things, they're IP addresses. I know that they talk to other IP addresses. That hasn't done me any good by doing it this way. I haven't learned anything from this visualization other than crap talks to each other. The same deal here. Email forwarding, email forwards. That's enough lines where I can go back and just read that. I don't need to go through the trouble. Same deal, not enough data depth. You just don't want to make your systems any more complex than they have to be. All right. So, what does make good visualization tool? Presentation is really important. A lot of people think of presentation as just aesthetics. Good presentation will make or break your analysis, whether it's text or whether it's visualizations or whatever you're doing. The presentation is really important. It has to be easy to use, and we've kind of covered that briefly. I don't want to spend time having to figure out how to use my tools. And probably the most important part of this is good underlying data structure. Whether you're displaying text, whether you're doing visualization, unless you've pre-formatted this data somehow, you're not gaining value from looking at it in an aggregated fashion. I haven't learned anything by just looking at lines of text. Or if I just have 20,000 IDS events, if I plot every single IDS event, I still haven't learned anything. The machine's done no work for me. It hasn't added value that way. You have to figure out what data you want to look at. Why am I drawing? Why am I visualizing this? So we'll cover some of the areas that we've dealt with briefly. Some things to keep in mind if you're building visualization. Logical distance doesn't have to be represented by real on-screen distance. A lot of times we'll see, hey, well, this machine's over in Asia, this machine's over in South America, so let's take up the whole screen to show that relationship. Don't have to. You kind of know that. That's typically not going to be important to the analysis you're doing. So when you're displaying data, you want to make sure you're only displaying points of information that you really care about. You don't have a lot of depth here, whether it's text, visualization, limited amount of space, limited amount of information. Don't plot things that just don't matter. You can also use multiple graphs to add data depth without clutter. Rather than doing some of the 3D graphs you saw earlier, you can get a lot more information there if you just use 3 scatter plots. You can see the data better, you can manipulate it easier, still get a lot of information. So color, again, goes back to aesthetics, and it's really underutilized and underappreciated. It's the one method you have on screen of communicating information that takes up no space. You've added data depth to what you're looking at and your ability to analyze information without losing any space whatsoever. Color can also be switched pretty easily. You don't have to rearrange things. Your picture could stay the same. You can cycle through colors. For IDS analysis, we'll color it by source IP, destination IP, IP combination, event name, whatever, just to rapidly get a comparison set that you might not be able to get easily by just rearranging the data all the time. Also, your color choices aren't arbitrary. If you don't choose the right colors, and we'll show you an example of this, it just hides information. A categorical color scheme is such that the closer the value is, the more disparate the color is. So if you have values 1, 2, 3, your color is going to be red, green, blue. A normal scaled color system would be 1, 2, 3 would be represented by dark blue, light blue, blue. That sometimes you want that distinction, sometimes you don't. It really depends on your data set. If you light to dark ranges, higher, lower values, like if you're measuring count, you can go light to dark and get high count, low count. If you're measuring importance, high count to low count. If you're, a rainbow range is useful for IPs because the side of the scale doesn't matter. With your count value, with your temperature values, whatever you're measuring, use light to dark if one side of the scale matters. Okay, so size is pretty obvious. One of the things that we've done with visualizations is we haven't seen people take advantage of size fully. One of the useful things for it is to be able to scale. Sometimes seeing those minor differences is really important. Sometimes seeing them just clutters information. So being able to scale the difference between your top value and your bottom value is super important. Jitter is also important. A lot of people didn't know what that means. Jitter is simply the random placement of points on a screen. So if you're going to overplot something, with 400 million events, we obviously do. In the earlier graph, we didn't overplot, but we could have. And that's, the exact position of that dot doesn't matter. So we'll maybe move it over on the x-axis, move it over on the y-axis, kind of get a view of what's underneath it. Zoom and focus. Analysis is an iterative process, as everybody's pretty much aware. If you have to manipulate stuff, you just want to manipulate it. The process shouldn't ever interfere with core purpose. You want to be able to select information, add information, combine it, find an intersection, all without having to recreate your graphs from scratch. And this kind of is harping on the same point, but we run into it time and time again. If I'm looking at multiple graphs, this data set should be connected to each other. I don't want to highlight something in one graph and have to go find that same information on another. That takes time, takes effort, you lose track of where you are. When you select information, all related information should be picked up. Where am I? So you need to be able to search, obviously. Text analysis is still important. You can't just do things based on the visualizations. You need to be able to search for specific data points. Same goes for memory. If you've done 300 sub-selects of a data set, you don't really want to have to go back to your starting point, have to figure out where you were and replay that. You want to be able to save your place. Information integrity, when we're doing this, I said earlier that we should be massaging the data. Whereas if I'm going to aggregate by hour, let's make sure that we don't include information that we've not aggregated on. I've run into people in situations where they'll aggregate on destination port and the IPs, and they'll not aggregate on source port, but they'll include that information anyway. They lose information. Bad thing. And you need to understand that you're always looking at a data subset. If you're looking at all the lines, it would be just too hard to see. But at the same time, it's not all the information. So the visualizations don't solve problems. It's how you format it. For example, we include source and destination IP as a single data token rather than include separate. That intersection is important by itself without caring what the IPs are. So we actually have a value just for the intersection of IPs. Kind of subtle, kind of small, not that important, helps out a great deal. And obviously aggregate. Problems with visualizations. Obviously, if you only have 100 events a day to one sensor, you don't need to do it. You don't gain. If you have 10,000 events a day to 10 sensors, then suddenly, summarizing this information display is really useful. You're always going to miss the one-offs. You have to create a correlation engine for the only one signature tricked ever type of stuff. And not even a text or view event correlation is going to catch all of your one-offs. You have to accept at some point that you're going to miss information. Another thing that we've run into with visualizations is your data source is really important. Some vendors really tokenize behavior poorly. And I'm going to pick on Dragon here in particular. They have a very, very archaic signature language. It's cool to be able to see the data, to go in with packet level data, but they don't tokenize behavior. There's no concept of 2 ports. I can't say in a Dragon system, stuff going to 6700, but not sourced from 22. So what I'm going to end up with, if I'm doing looking for any text string in that, is I'm going to false positive on SSH connections constantly because it's just a random string of characters. When you look at Dragon data, it looks like noise. When you look at some of the other vendor data, they tokenize actual activity a little bit better, get better displays. More information can be better. We tend to run a noisy, I guess, implementation, and some of it's don't want to take the time to completely tune it. It takes time. But the other side of that is, especially with like host-based intrusion detection systems, all those are audit systems. There typically isn't like bad signatures. So if I look at everything over time, it's very, very easy to see changes in behavior. If a Windows server starts acting differently, it's very, very easy to see that. In fact, considering detuning some of the IDSs just to get some idea of what's going on. So we're going to go through some, I'll go interactive in a moment, but this is some of the research graphs we've done. You're looking at probably 2 or 3 weeks worth of information from across the planet. What this provided us with some information. It seems kind of basic. Each dot represents one destination IP's count for an hour across time. So you have y-axis is going to be count, x-axis is going to be time. What we're looking for to see if there's some threshold of normalcy. Well, we couldn't programmatically determine it, but I could look at this data and kind of go, I don't know if you can see the pointer, but over on the left-hand corner, about a third of the way up, above that normalcy kind of stops. Things become one-offs. And we could call it there, or we could call it kind of an 8 here. Events stop happening at a certain frequency. There's enough, like maybe it's just I haven't looked into it enough. Maybe it's just Windows traffic that generates that much noise. Maybe it's some other automated thing. But at some point, your frequency becomes abnormal. It would have taken me ages to code this and to find that value. But I can pretty much look and come up with a couple of suggested points for thresholds. A couple other things we picked up is that somewhere on the network we actually have, if you notice, every other line here is denser than the others. It turns out that they're mistakenly multiple IDSs watching the same network segments. So weren't looking for that, just grabbed the destination IP frequency, ended up fixing network problems, or at least deployment problems. By the way, the y-axis is logarithmic. That's why you see the bands and it kind of scatters up. Third thing we saw, and you may not be able to see this, I can't tell from this angle, is up here. There's a band of dots that kind of goes like this. And it turns out that that's 0000 as a destination, which most of the IDSs will use for scan destinations. So what we can do based on that information is look at that going, hey, that's neat. Let's track that destination across our customers over time. I can look for worm or other automated activity outbreaks just by looking at that destination IP without having signatures for it, without knowing anything other than, hey, the whole planet's starting to scan a little bit more. Don't care where it's going, don't care anything about it. Another frequency graph, which is particularly my favorite. On the y-axis, we have destination port scaled logarithmically. So from here to here, roughly, or about this top third is above 1024. Below is under 1024 for ports. And again, it's count scaled logarithmically on the x-axis. A couple things we didn't really expect is the damage peer-to-peer does to monitoring networks. These two features right here, this is in a typical peer-to-peer destination port range. This is the client side traffic for that. The bulk of information, and really would not have thought this, if IDSs are not tokenizing peer-to-peer behavior very well, or anything else. It trips, massively trips all the time, and there's just that much volume. The other piece of this graph that was interesting is that if you look at below 1024, there's not a lot of data on how well you can see it. There's only a few points there. IDSs do a good job of tokenizing normal trusted services. So we can go forward and react differently to any event that's above 1024 than below. Below 1024, my confidence goes up a bit. I kind of trust, based on its behavior, that it's a little bit more accurate than stuff that's above. Again, we talked about tuning briefly. You're looking at 3 days worth of tuning in these 3 graphs. They're both representing the same data set, and they're all tied together. You can just look at total volume in this left-hand graph here. It kind of drops down almost nothing. You can see we did it. These are events in the middle graph over time. Didn't turn a lot off, most still stay there. So we really focused. Without reducing your total visibility, kind of went down. Didn't have to turn a lot off, but completely dropped the volume down. And the right-hand graph is really just related to the left-hand. You're looking at count over time. Some other one-off type of stuff is, we talked about categorical color earlier, and this is firewall behavior over time. Each color here is a specific firewall rule that's been triggering. Somebody came back with a question, hey, this is a co-managed firewall. We think somebody made a change. We don't know when, but we're requesting updates to specific rules, and people are updating them, and it's not matching up. The rule we thought we were having you update isn't updated, so has anybody made a change? We created this right-hand graph for them first. And if I had done a pastel color set, this would have been a solid blue, because these are one-off. These 2 rules are one-off from each other. Did it with a categorical color set, and see immediately, hey, somebody changed it. Went ahead and created the graph on the left. Y-axis, you're looking at particular firewall rules. X-axis, you're looking over time. Pretty much, you can look halfway down and see this white line here. Never fired before, doesn't behave quite the same as the rule above it. Looks like somebody inserted the rule there. You can confirm and watch how everything kind of drops one below for the rest of the data set. That would have taken us a fairly long time to do just by going through the text firewall logs, looking for when somebody put in the change. I just have access to the logs of the events, don't have change logs. Using visualizations has been interesting to tie together HIDS and NIDS data. We'll tie 2 data sets together, and that's what this graph is representative. These are kind of useless. They're actually just pretty, but they tie the data set together. You can select HIDS information and find all of using visual tools, all the related IDS information. So if you're looking for things that got to the firewall, things that got past that, and then things got to the host, you can use the visualization system to kind of tie those together. All right, let's go into some of the actual demo. Okay, so we talked about using multiple graphs. What's cool about the multiple graphs thing is, I don't know if you'll be able to see it, but if I highlight, you're looking at events over time here. Right now we're colored by source IP. You pretty much swap up what our relationships is up here. So let's maximize that. So now you look at how the destination port behavior changes within the data set. We talked about linked data sets, and this is why it's important, because we have these, 7 graphs here. And in this upper right graph, we have 1, 2, 3, probably 4 dimensions of data: event, time, count, and destination port at the moment. That size is small enough to see the more interesting of the patterns. but we want more graphs. I want to see the destination port, I want to see the source port, I want to see the IPs, all of that type of thing. This information is all linked. If I decide that some section of this is interesting, go in, highlight it, all the relevant data and all the other graphs is interesting. Dive back down into it. We talked about scaling earlier. Okay, so that's kind of a low view. So let's scale up the counts. Okay. If we were to go into store the data set, reselect. Wish you could see. So some of these things are pretty much readily interesting. For me, looking at this cluster right here, if you can see it, hasn't happened before, hasn't happened after. Not a lot of volume, but it's pretty visible in this data set that, hey, that's kind of really anomalous. Grab it down. Pull it up. Scale it up. It's essentially what we grab is a bunch of RC traffic that hasn't happened in, I don't know, this is from I think this data set's like a week or 2 weeks or something. So we could pretty rapidly go, this stuff hasn't happened, it's interesting. Grab the specific events now that we've grabbed the larger pattern. Pull it up. And I'm not going to pull up the IPs, but what I would go ahead and go through after this is actually graph out which IPs was talking to who. That saved a huge amount of time. Might not have ever noticed those IDS events or those IRC events in the stream of traffic. If we were to go through and do this same behavior for tuning, tuning IDSs, you could actually grab a bar chart pretty quickly, turn around, find out what the most periodic events are. Grab down. You're looking at events, just how many hours it happened, not total count. Grab them. Kill it. So then we go ahead and color it by IP pair. And so we have a beginning place to look for events that we're going to tune out of the data set because they happened from February 10th to February 23rd. Some of these happen every single hour. Of every single day. That's been helpful. That's pretty much the demonstration, the talk. A little bit early. So do I have any questions? Or?